In this video we're going to take an informal look at the divergence theorem. So the idea is that if we had some surface here which enclosed a volume, then we could find out the flux through this entire surface. And there's the equation there for our flux, which is the normal component of a vector function over the entire surface. So that's the flux over the entire surface. So then if we were to look inside this volume and we were to split that into small volume elements here, and then we were to look at the flux through each of the volume elements, and then if we were to look at an infinite number of these elements and add up all of the flux, then we've got the equation below. So we're going to have the flux through some surface, okay, say for example that surface there, is the normal component of the vector function f over s. And now if we were to then add up all of these components of the flux, then we would be summing L equals 1 to n. N is the number of faces of this value here of the flux. But then if we were to note that if we stuck two of these volume elements together, then the normal component would be in this direction here at S0, and also this direction there, the opposite direction at S0, where both of those surfaces join together. So we could see that the flux in one direction will cancel the flux in the other direction. So if we add up both of the flux S0, the entire flux is going to be equal to 0. Now if we were to then add up more and more of these surfaces, we'll notice that these volumes, we'll notice that the surfaces where they connect, the flux is going to equal to 0. So it means that if we continue this up until we build up the entire surface, the only flux that's actually going to count would be the flux that actually on the surface of the yellow surface here, okay, which would be the flux over the entire surface. So kind of stated in word, we're really saying that there's a cancellation for all of the adjacent subvolumes, the subvolume surfaces. So all subvolume surfaces are adjacent to two subvolumes except for the outer surface. Okay, so that's really just a statement of what we've seen here, okay, and extended to an infinite number of volumes up here. So that's really in essence what the divergence theorem is. But so let's continue with it. So if we were to write this surface integral here, and then if we were to add up all of the other surface integrals, but we'll multiply by delta v and divide by delta v. So in doing so, we can see the stuff that's in the brackets. That's just the divergence of that field. So then we can write down here that if we were to take this here, and if we were to take the limit as the number of those surfaces tended to infinity and the value of the volume element tended towards 0 of this divergence, then we would just have the triple integral of the divergence. So all we're really saying is that we'd have the divergence at a point, and then if we were to find, we could find the total divergence by adding up the divergence over x, y and z direction, and that total divergence would just be the flux through this surface. Okay, so that in effect is the three-dimensional divergence theorem. So divergence theorems relate, in this instance, surface integrals in 3 dimensions, surface integrals to volume integrals. And there's a related quantity. The quantity here is the divergence of the field, and here it's the flux in the field. So we could really say that the mass flow rate, or the flux through the surface here, is equal to the mass flow rate per unit volume when we sum up the entire volumes. Okay. Now that's the divergence in 3 dimensions. You could look at the divergence in 2 dimensions, and it would relate surface integrals to line integrals. And then you could look at it in 1 dimension, which would just be the fundamental theorem of calculus, which would relate differentiation and integration. So possible to do another video detailing that stuff in more mathematically precise detail. Okay, so but that's enough for now, and that's the divergence theorem that we're going to be using. So let's look at a couple of applications. So the first application is in terms of the electric field. So we've seen that Gauss's law can be written like this here, and on the right hand side this is just the total charge upon epsilon naught. So that's the charge per unit volume integrated up over the entire volume. Okay, so it means that from the divergence theorem we can see that these surface integral can be related to the volume integral by the del operator. So we would have, we can replace this here with our del dot E. So that means that this thing here is going to equal the triple integral of the maximum, the total charge. Okay, so we're going to end up with our triple integral of the del dot E is equal 1 upon epsilon naught triple integral of rho dV. So this can then be rewritten as del dot E equals rho upon epsilon naught. Okay, so that's just another little derivation of the Gauss's law, which we've seen in the previous video using the divergence theorem. So let's look at a second example. This is the continuity equation. So let's say we have some substance, say water, flowing through some volume. So we have the water density, or the density of the material or liquid. So it's a mass per unit volume. And we have some velocity of the substance as well. So that's velocity as a function of x, y, z and t. So we're asking the rate at which the substance and the volume is changing. So the total amount of substance in the volume is the mass per unit volume integrated up over the entire volume. So that's the total amount of stuff. And we're asking what's the rate of change of that stuff with respect to time. So we differentiate that with respect to time and we get this little equation here. So we know the rate of stuff that's flowing through the surface from the idea of divergence is going to be given by the surface integral, and we used this very method in order to derive the surface integral a couple of videos ago. So the rate of change of stuff in the volume is equal to the rate at which it is flowing through the surface. Okay, so that's the rate of change of stuff in the volume, and that's the net flow through the surface, and it's negative because it's a flow into the surface. So all the stuff in the volume must come through the surface. So then we can say by the divergence theorem that this flow through the surface is equal to the entire stuff in the volume. Okay, but this entire stuff in the volume is going to be replaced by del dot rho v via the divergence theorem. So then we can rewrite this out in this form here, and the triple integrals disappear, and we're left with our partial rho by partial t equals minus del dot rho v. So we can rewrite this equation, bring this across. So partial p by partial rho by partial t equals plus delta del dot j equals 0, where this idea j equals rho v is the current density. Now it's quite a quick talk through that. That's called the continuity equation. We'll come get up against that in other places, so whenever we do the full course in electromagnetics we'll see this in more detail. So I hope this was of use. If it is, then don't forget to subscribe, and I'll see you on the next video. Okay, goodbye.